Hello and welcome to this course on Introduction to Polymers. We are looking at the concepts of polymers, their properties and usage, and also sustainable aspects of polymers. In the week one, we are trying to answer questions related to polymers and their unique features related to the structure of polymers. And in this lecture, we will look at the essential relations which are there in polymers, which are called process structure property relations. So what do we mean by structure, what do we mean by process, and what do we mean by properties, and how they are all interrelated will be the learning from this particular lecture. And the focus in this lecture will be on concepts. And how we are going to do this is by looking at what is processing in the context of polymers. What do we mean when we say we are processing the polymers? What do we mean by structure of these polymers and properties, and more importantly, how are they interrelated? So we'll look at some few examples of process structure property relations in these polymers. Let's first begin by trying to understand what do we mean by polymers and what is the diversity of materials that are actually there when we talk in terms of polymeric materials. So we can process the polymer by itself, or we can have the polymer made up of different monomers when it's called copolymer. We could mix polymers and make them into a blend. We could also mix the polymer along with another filler, a fiber or a particle, and in which case it's called a composite. We could also have a polymer membrane, for example, for water purification. We know that many of the RO units which are there in our homes, or whenever we talk of purification of water, membranes are used, and quite often many of these membranes will be porous, in which case they are either filled with liquid or gas. Can you think of an example of a gas-filled polymer? Styrofoam, of course, right? You can see that it's a very light foam material where polymer and gas is together. And then we could also have a polymer along with some charges. So in which case it's a complex of polymer and charge. So when we say polymeric materials, there is a variety of materials, diversity of materials that are out there that have to be considered. And sometimes polymer by itself is there, but quite often it is mixed with other polymers or other sets of substances. So now what do we mean by processing of these polymers? So we could have a variety of ways in which polymers can be processed. For example, we can melt the polymers, which means we increase the temperature. So the one aspect we can look at is where we can melt the polymers, and by which we mean we increase the temperature, make them more fluid so that they can flow, and then mold them and so on. So what we have is melt of a polymer and then it will solidify. So this is one aspect of processing. This is how a complex shape can be made. If you want to make a disc, let's say disc-like object. So initially we start with granules, we melt it and then make it into disc shape by making it flow into a disc shape mold. And of course, as I talked about different shapes, once we get a shape, we might have to manipulate the shape further. So for example, we start with granules, we extrude a wire or a fiber, and then we may want it to make it thinner, or we extrude a sheet and we may want to make it very thin film. So in that case, we have what are called shaping operations. An important class of polymers, we start with what is called a pre-polymer or a resin, in which case the polymer is only an oligomer or small molecular weight, small molar mass molecules. And then when we are actually processing and shaping it, curing happens or reactions happen. And so in this case, solidification happens because there is reactions happening in the material. There's alternate ways of processing polymers also. For example, if we are using in food applications and we want viscosity to be higher like a jelly in a jelly, in that case, we may be using what is called a solution processing. So quite often, let's say in coating operation also, we want a polymer coating as a protective coating. Then what we will do is we will form a solution, we will dispense it on the substrate where we are coating, then we will allow the solvent to evaporate, and then the solid coating will form. So again, this is an example of a processing operation. We need not have solution of polymer where there is an intermolecular mixing. We could have just polymer particles, like in case of paint, where we have particles of polymer, particles of pigment, which is usually an inorganic oxide in a solvent. So this is called dispersion. And of course, when we are looking at engineering of these materials, we may have to cut, we may have to shape, give it a particular shape, we may have to join, welding may have to be done, or fastening may have to be done. So many of these machining operations are also required as part of processing. And another aspect of, we have to make solution, emulsion or dispersion, we will have to do mixing and cooling, heating and all of these operations. So when we say we are processing polymers, we are basically trying to fabricate objects out of these polymers, and as part of the fabrication process we have flow, we have heating, cooling, we have mixing, and we have applications of stresses and application of several basically applied field, so that we get a requisite shape that we want at the end. So this is called processing of polymers. What about structure and properties? In case of polymers, basically there are two sets of states which are most important. And one important feature you can notice here is I am not calling them liquid and solid. I am calling them liquid-like and solid-like. And this is something which we will have to continuously learn during the course, that we will have solid polymers which will have some liquid-like features, and we will have melt of a polymer or a solution of a polymer which will have some solid-like features. So that's why rather than calling them solid and liquid, we will say they are more solid-like and more liquid-like. So for example, a liquid-like state which could be a solution or a melt or even a rubber, by the way, has many features of liquid like phenomena, because polymer molecules are dynamic objects in these situations, which means polymer molecule can move around. And if you think of a bowl of noodles, basically the noodle are moving around, and then you can think of a liquid-like state of polymer. So therefore, the macromolecules or segments can move about. So there is a segmental motion possible, or macromolecules can change conformations. And when are these important? For example, when I am looking at diffusion of a small molecule through a polymer, then how the small molecule diffuses around these macromolecules which are also moving about is an important consideration. Or when, let's say in a diaper where it's supposed to absorb, how much can it absorb? How much can it swell? And that is determined based on how much is the dynamics of the polymer, how flexible it is, and so on. Similarly, when I make some object out of PVC, polyvinyl chloride as a polymer, I can make objects out of PVC only when I plasticize it. So I can add something to plasticize it, I can heat something to plasticize it. Whenever I plasticize something, I make segmental motion possible, macromolecular conformations possible. So these are liquid-like features which we will have to understand. And of course, I have already highlighted the fact that when it's liquid-like, it will certainly have some solid-like characteristics also. So viscoelasticity, viscous, elastic. Viscous means liquid-like, elastic means solid-like. So viscoelasticity of polymers, the key feature associated will be polymer dynamics, which will give it the liquid-like characters. On the other hand, if we look at solid-like materials, then we need to know whether it's crystalline or amorphous material, what is the orientation of macromolecules, what are the ways in which molecules are arranged with respect to each other, or if we have a fiber and a polymer, how is fiber arranged within the polymer matrix, and so on. So it's called the microstructure of the material. So this is also an aspect of structure of these materials. And the properties which are of interest due to the structures are, for example, the deformation of a polymer material. So if it's more crystalline or less crystalline, it will be easy to displace molecules or more difficult to displace molecules. So therefore, mechanical properties will depend on the microstructure and how crystalline the material is. For example, conductivity. And in this course, we will learn about conducting polymers also. So whether crystallinity will enhance conductivity or whether amorphous material will enhance conductivity, we will see structure is again closely linked with property of these materials. And in the solid state, though molecules seem to be frozen and therefore we get a solid-like character, there is some liquid-like motion possible over long term or at high temperatures. Then therefore solid-like materials will be viscoelastic, which means they will be predominantly solid-like with lot of elasticity features but with some viscous features also. And of course in solid state we also have to worry about, for example, can oxygen come in, is it resistant to UV radiation, are chemical reactions happening in the solid state, because this will determine the overall performance of the polymer. So in a nutshell, we have seen what is meant by processing of polymers, what is its structure, and what are the properties. Now all of these are interrelated to each other. So generally this is called a process structure property triangle of the polymers. This is not unique to polymers, by the way. Most material scientists would talk of process structure property relations in the material, because the way you process them will determine their structure and properties, or depending on the structure of the material, processing and properties will be determined, or properties will determine what process and what structure do they have. So it's basically interrelations between all of these. When we say processing, we talk about what was it heated to, what was it cooled to, what was the thermal history of the material. When we talk about processing, because we stretch the material, we make it flow, and of course when we process it, it could be along with a plasticizer, it could be along with a solvent. So there is always a physicochemical, mechanical and thermal history associated with processing, and two different processing operations will therefore lead to two different sets of structures and therefore different sets of properties. When we say structure, we look at the molecular structure in terms of arrangement of molecules, in terms of domains, whether it's crystalline domain or amorphous domain, or maybe one particular polymer mixed in another polymer, and also whether there is gradation in terms of, there may be compositional difference. One part of the component may have lot more fiber compared to the other part. So therefore there is a gradation in terms of structure. One part of component may be more crystalline compared to the other part. So that's why it's called microstructure. We many times refer to not just structure but microstructure, because in this case we are interested in microscopic details of the structure. And when we think of properties, of course, we think of all different properties: thermal conductivity, mechanical modulus of the material, conductivity, refractive index, and so on. So now, in the beginning, we looked at what is meant by process structure properties. Now we will close this lecture by looking at few examples of each of these as to how processing, structure, and property are related in case of polymeric materials. So let's start with processing and structure relationships. The first example that I'm going to give is biaxially oriented polypropylene, BOP. If you search this term, you will see that lots of suppliers are there in each and every country which supply BOP films. And it's different compared to polypropylene. And the reason is that this film is processed in a particular way. What we mean by biaxial stretching is, if I get a film, if I stretch it in two perpendicular directions. So what can happen during such a stretching operation? Remember that if I zoom in to this, what I might have is basically the macromolecules that I have talked about so far. Now what happens to these macromolecules when they are getting stretched in two perpendicular directions? How is this different compared to if I take a film of the same polypropylene but stretch it only in one direction? Clearly you can see that the segments of these macromolecules will start aligning due to stretching. And alignment will be very different if it's this kind of stretching, which is called uniaxial stretching, as opposed to this type of stretching where we call it biaxial stretching. So that's why what we have in this case is biaxially oriented polypropylene. And given that the molecules, macromolecules and segments have been oriented biaxially, the properties are far superior compared to just making a polypropylene film. And that's why this is such an important product. And you can see how in this case processing is influencing the structure, the orientation within the polymer. Now let's look at an example where structure influences the processing. And branching is a very important indicator of how a material can be processed. So it's a structural feature that determines the processing capability of a, let's say, polyethylene. So what is needed for a good processing of polyethylene is controlled extent of branching and also the length of branches. So low density polyethylene is easier to process to make thin films compared to high density polyethylene. So branches in some ways help. Now the question that you could ask is, why is this the case? So again, if we have a low density polyethylene, it's something like this, where there is very long branches on the backbone chain. And of course, we will never have one particular molecule in isolation. We will always have multiple such molecules. And so what we have is basically another giant molecule with lots of branches also entangled with this molecule. And so with all these molecules entangled with each other, how the entangled mass of this polyethylene, branched polyethylene behaves when we have make it molten and then making it flow for making a film. And how is this different compared to, let's say, an HDPE, where you have largely linear polymer with very small fragment at most, and this is entangled with other sets of macromolecules. And you can clearly see that how a molecule can move about will be very different, because entanglement and these branch points will make very different motion in case of branch polymers as opposed to linear polymers. And so therefore, for a controlled production of polyethylene films, many times blending of branched and linear polymer is done. And this is such a popular case of improving processing of materials that polylactic acid, which we will learn is a very promising biodegradable polymer for many of the packaging applications. But it's very difficult to process polylactic acid. So one of the key research question and practical question people are asking is, can we use branching to improve the polylactic acid processing? Polylactic acid generally I get will be a linear molecule. So can I make it branched? Or can I mix some other branched molecule in it so that I can make film very easily, like I can make films with polyethylene? And further on, another aspect that we will continue to learn throughout this course is related to when we are saying polylactic acid, in which way is it biodegradable? What makes polylactic acid biodegradable and polyethylene is not biodegradable? And also, why is polylactic acid important? Because we are using renewable resource with it. So in next set of lectures during the course, we will also learn about these aspects. Now let's continue and look at the other examples of processing and property. For example, when we are doing welding, molding of plastic objects, we will have flow. So when we do plastic molding, there will be flow. And melt flows. So for example, if we are making a cylinder with a hole in it, so basically an annular kind of object, then what will happen is we will have a solid block around which polymer will flow. So polymer melt will flow like this, it will flow like this. And so the polymer in this region, polymer melt will come and flow and again join together. So that's called a weld line of a mold. So weld line is going to be the weak spot, because two polymer melt fronts have to come and meet, and then of course macromolecules have to start entangling. But depending on the diffusion rate and depending on the temperature and pressure of our molding operation, this interpenetration may not be sufficient. So in the end, when we get a plastic object, everywhere else the properties will be very strong, but here, since the polymers haven't got enough chance to intermingle and interpenetrate, there will be a weak spot. So this is a case where processing is leading to a property issue in terms of weak spots. and that's where the part is likely to fail. So we need to know where the weld lines are, and can we reduce the disadvantages of weld line, can we improve properties around weld lines, so processing directly influencing the performance of a part. We can also look at other example where Muni viscosity of rubber is important in terms of finding out how will we process it. For example, how much time will the molding operation take? Because when starting viscosity will determine how the material is flowing and being shaped inside a mold. And more importantly, in case of rubber, as the molding is going on, cross-linking happens and viscosity changes as a function of time. So cross-linking reactions happens and rheological properties, which are nothing but flow behavior properties of rubber, keep on changing. And so we have to ensure appropriate amount of flow during processing so that we have complete filling of the mold, which implies that we should not have incomplete filling, or we should also not have too much overflow. And this can be ensured if we make sure that we understand the viscosity of the material, the property of the material properly. So in this case, the property of the material influences the processing conditions. Let's complete the overall consideration by looking at the property structure. And as we will learn during this course that it is possible to get a conducting polymer, the example I have given here is called P.PSS. You can search for it and you can find a lot of information related to P.PSS. In fact, it's available as ink. So I can use an inkjet printer to actually print electronic devices using P.PSS. Very interesting, isn't it? So the repeating unit in this case is ethylene dioxythiophene. And it is mixed with another polymer which is called polystyrene sulfonate. So it's a very complex material, and the conductivity in this depends very strongly on the structure of the material and in fact the microscopic arrangement in the material. So how is the crystalline arrangement of P dot, which is one polymer of this overall polymeric material, and how are the domains of P dot and PSS distributed with respect to each other? So you can see that how structure of the material determines its property, in this case electrical conductivity. And this gives a very rich possibility from an application, from a scientist and engineer point of view. Can I manipulate my structure in a way to give me maximum property? So I need to understand the relation between what is the microstructure and what is the property, in this case electrical conductivity. The last example we will look at is where a property, in this case glass transition temperature, influencing the structure, and in this case molecular rearrangements in the material. So a polymeric material, let's say PET bottle, if we keep it at room temperature for 25 years, at room temperature means around 25, 30, 40, 30, 35 degrees Celsius, maybe 25 years it will be fine. But what if it is also subjected to 50 degrees Celsius? Will there be any molecular rearrangement? Will its structure change? And that depends on its important property called glass transition temperature. And given that we will see that polyethylene terephthalate, the PET bottle, the glass transition temperature is around 80, at around 60 degrees Celsius and around 55 degrees Celsius, structural changes are possible. If we take a polymer whose glass transition temperature is 150 degrees Celsius, then at room temperature, no structural changes may take place. So clearly you can see a property will determine what is its microstructure going to be over time. So in case of many of the polymers, rearrangements will take place depending on the difference between its glass transition temperature and whatever is the service temperature. So through this, what we have seen is possibility of important correlations between processing structure and properties in these polymeric materials. Just to remind you that conducting polymers we will look at in a separate lecture, where we will see is it possible to get conductivity? Rather than adding a conducting material into it, can I have polymer which are intrinsically conducting? And sure enough, we'll see those later. And of course, glass transition is a very important property in polymers. And we will devote a couple of lectures discussing in this much more detail. So with this, we have come to the first three set of lectures, in which case we try to understand some basic nomenclature associated with polymeric materials. Thank you.